Now that we have discussed load path for lateral loads and have laid out a process for analysis, let's take a closer look at how to calculate the load that gathers at each diaphragm. Pressure acts on the wall, and as we discussed in a previous video, the wall is supported laterally by the foundation and the diaphragms. This is a sketch of what is actually happening. If we idealize the wall as a vertical member, the best idealization is a pin support at the foundation because the wall doesn't move vertically or horizontally here. At each floor diaphragm, the floor will move horizontally some, so the most accurate idealization is springs at each diaphragm level. We can analyze that, but it is a complex and time-consuming process. If we look at how much the floor diaphragms deflect horizontally, it is typically much less than the wall moves horizontally between those diaphragms. So we can make a reasonable idealization that is more simple, but reasonably accurate. We idealize the foundation as a pin support and roller supports at each diaphragm level. So we typically consider the actual loading on the structure as acting on a vertical member with pin and roller supports. To be clear, the assumption we typically make is that the wall is much more flexible out of plane than the members that support it. That results in the idealized wall we just drew. To analyze the wall, we typically consider a vertical strip of the wall. That strip has unit width, so a width of 1. Pressure acts on the wall, and that pressure has units like pound per square foot or kilonewton per square meter. When we integrate that pressure over the width of the strip, it is effectively multiplying the pressure by the width, which is in units like foot or meter. The result is a distributed load in units pound per foot or kilonewton per meter. But this distributed load is for the unit strip. If the wall is supported at only the foundation and roof, the idealized wall is determinate. That means we can use equilibrium to find the load being transferred at the roof and at the foundation. If we follow units, the idealized load is distributed, so it has units force per length. When we apply equilibrium, the reactions will be in units of force, but they are for a unit strip, so the reaction is actually a distributed load. It has units like pound per foot or kilonewton per meter. The horizontal reaction at the roof level is the distributed load acting on the diaphragm edge. If the wall is supported by multiple diaphragms, like in a multi-story building, the idealized wall is indeterminate. To analyze this idealization, we can use detailed analysis methods covered in later chapters. Depending on the loading and how many diaphragms there are, this can be a time-consuming process. More often, we use approximate analysis. That tends to provide reasonably accurate results. The approximation we make is to treat each segment of wall as acting separately, meaning each story of wall acts independently. Consider this idealized multi-story wall. We treat each story as an independent structural segment. For this example, We can break the wall into 3 segments. The top segment is simply supported with a cantilevered end. But there is another reasonable way to break up this wall. We can break the wall into 4 segments. The top segment is a cantilever above the roof level. The 2 approximations will give slightly different results, but both give reasonable approximations. If the pressure on the wall is uniform, we can use tributary heights to calculate the resulting load at each diaphragm level. This bottom level is simply supported with uniform pressure. Equilibrium tells us that the reaction at the bottom is that pressure times half of the height of the segment. So it is the pressure times the tributary height. For the first diaphragm, there is pressure coming from above the level and from below. So the tributary height is from mid-height of the bottom level to mid-height of the next level. We repeat this for the second diaphragm and for the roof diaphragm. The distributed load at diaphragm level is the pressure times the tributary height and will be in units of force per length. Of course, we could use equilibrium instead. For uniform pressure, we get exactly the same results as long as the top segment is treated like a cantilever. If the pressure is not uniform, meaning not constant for the entire height, we must use equilibrium.